And now, please welcome to the stage, Sophia Ekonomou.
Welcome to the short plenary session. The first talk is by Fermi Ma, and he'll tell us about how to construct random unitaries.
All right, thanks for the introduction. All right, so yeah, this is how to construct random unitaries. This is joint work with my wonderful co-author, Robert Huang. Oh, sorry. Is there? All right, so this is a talk about random unitaries. Now, typically, a random unitary refers to a Haar random unitary. And so I just want to start by reminding you the definition of the Haar measure, which is it's the unique unitarily invariant measure on SU2 to the n, the space of all n qubit unitaries. And what this means is that for any fixed unitary W, if U is sampled from the Haar measure, then WU is also distributed according to the Haar measure. And so Haar random unitaries are really everywhere in quantum information. They're fundamental to understanding a wide range of quantum phenomena, from information scrambling to how you generate entanglement, to understanding the behavior of random quantum circuits, to questions about unitary complexity. The list goes on and on. But one fundamental challenge we face when working with Haar random unitaries is that, like, by their very nature, they are exponentially complex. Right? So they require an exponential number of bits of randomness to even sample. And not only that, if you take a Haar random unitary and you look at the minimal size quantum circuit for implementing that unitary, it's going to be exponential size. And so this makes them completely impractical for nearly any interesting application. So this motivates the notion of a pseudo-random unitary, first introduced in this work of Ji, Liu, and Song. So pseudo-random unitaries are efficiently computable unitaries that are computationally indistinguishable from Haar random. So a little more precisely, it's going to be a family of unitaries, so a set of unitaries U sub k, so indexed by a key k, where if you sample a random unitary from this family, then no computationally bounded quantum algorithm can distinguish this from a truly random unitary sampled from the Haar measure. And this notion of computational distinguishability here, I'm referring to efficient quantum algorithms that have access to the unitary as an oracle. So it has access to a button. Every time it presses this button, this oracle applies the unitary to a state of the adversary's choosing. And so the classical analog of this is either pseudorandom functions or pseudorandom permutations, so PRFs or PRPs. So it's been an open question for quite some time now to get provably secure PRUs. And by provably secure, I mean secure under standard cryptographic assumptions. So what do we know about this so far? Well, there were a number of proposed constructions. So in the original work of Ji, Liu, and Song, the proposal was perhaps like alternating a sequence of Fourier transforms with pseudo-random functions applied in the phase. There should be maybe more alternations here. But that alternating these like sort of back and forth would eventually lead to something that's Haar random or seemingly Haar random. A more recent construction of Mecker, Peremba, Hsin-Yuan proposed composing a pseudorandom permutation, so a pseudorandom permutation applied in place, mapping ket x to ket pi of x, with a pseudorandom function applied in the phase, with a random Clifford unitary. These aren't the only two constructions. There's actually a whole host of other constructions out there that are not on this slide. All right, so what did we know about security? The best known security we could prove before this work was non-adaptive security. And so non-adaptive security is a weakening of the standard security notion of a PRU, so that security only holds against non-adaptive distinguishers. These are distinguishers that make all of their queries to the unitary at once in parallel. So a non-adaptive distinguisher looks like this, this diagram here. Notice all the queries to U are made simultaneously. Okay? So this is certainly like a large and expressive class of distinguishers, but in general, a polynomial time quantum distinguisher has the freedom to query adaptively. It can make one query to U, use the outcomes of this query to determine what it queries next. All right, so in this work, we fully resolved this question. We showed that pseudorandom unitaries exist, ruling secure against all adaptive distinguishers, assuming that one-way functions exist, so standard cryptographic assumption. We actually use the same construction as Mecker, Peremba, Hsin-Yuan, this PFC construction, where you compose a pseudorandom permutation with a pseudorandom function, the random Clifford. So the real difference between our work and the prior work is in the proof technique. And our new proof technique is something we call the path recording oracle. And this gives a way to efficiently simulate a Haar random unitary. Now, if you don't know what I mean by efficient simulation, don't worry, I'm going to cover this quite extensively in the rest of this talk. But I'll just say that one nice bonus of this technique is that it really only uses basic elementary quantum information arguments, namely purification. Okay, in fact, we go one step further. In the original Ji, Liu, and Song PRU definition, the distinguisher is only allowed to make queries to the unitary u in the forward direction. So it can submit psi and get u psi, but it can't query the unitary in the reverse direction. And you could argue that if you really want to capture the spirit of an object that is black box indistinguishable from a Haar random unitary, you really should have access to the unitary in both directions, right? Anytime you have a circuit for a unitary, you can always invert every single one of the gates and generically implement the inverse. So you can ask, is it possible to get this stronger notion where you have security against distinguishers that can query both u and u inverse? We call this a strong PRU, and we also prove that strong PRUs exist, assuming one-way functions. And the construction is quite similar. It turns out you just need to tack on one more Clifford on the other side. And there's a minor technical detail where the pseudorandom function now has to be at least a ternary output pseudorandom function. So you'll have to see the paper for this. For this talk, I'm just going to focus on the weaker notion of security against forward queries. Right. So for the rest of this talk, my plan is I'll first talk about simulating a random function. And this will hopefully give you a sense of what I mean when I say efficient simulation. Then I'll explain how in this work we do efficient simulation for random unitaries using this path recording oracle idea. And finally, I want to do two things at once. I'll explain why exactly this path recording oracle is correct, how it actually simulates Haar random unitaries, and at the same time prove that PRUs exist. OK, so here's the warm-up. I want to talk about simulating random functions for just a few minutes. So no unitaries for the next slide. OK, so imagine you have a classical algorithm A that has oracle access to a classical random function f. So the natural way that you implement this is you sample the random function in advance, the entire exponential size truth table. And every time the algorithm wants to query the function, you just answer according to the truth table of the function. OK, so of course there is, if you would like to run such an algorithm, there's kind of an obvious way that you would speed up this process, which is this efficient simulation or lazy sampling approach, where the idea is you only sample the random function, you only sample as much randomness as you need. So you sample as much of the truth table as the adversary actually sees. And so this means that when the adversary queries the function on input x, you just make up an answer. So you sample a random y, and then you store this for later in case the algorithm ever asks the same x again, you have to reply with the same y. So this is called lazy sampling or on-the-fly simulation. And hopefully it's obvious that from the algorithm's point of view, these two are identical, right? Either it queries a truly random function, or every time it makes a query, you just make up a random answer on the fly. These are going to be the exact same distribution from the algorithm's point of view. OK. So even for random functions, I want to note that properly simulating the view of a random function, or of an algorithm that queries a random function, is already quite subtle if the algorithm can query the function in superposition. So in particular, if the algorithm can query any superposition of inputs x, not just a single classical x, but submit a superposition of x, like sum over x of alpha x ket x, and learn the output of the function in the phase. So it gets back the state where on every ket x, you've inserted this phase term, -1 to the f of x. If you'd like to simulate this, it's already quite subtle because intuitively, at least the naive simulation on the previous slide seems to require that the simulator knows the input x. It needs to know which, when it's time to sample a random y and when it's time to look something up. Here, trying to do that naively would destroy the superposition. If you tried to measure this to learn x, you would destroy the superposition. And potentially, the adversary would detect this. So already, simulation is quite subtle for random functions once you get into quantum. However, this was resolved in a very influential work of Mark Sandry, who showed that the right way to generalize the naive classical simulation to quantum superposition queries is with this technique called the compressed oracle. So unfortunately, I won't have time to say anything more about the compressed oracle, but I want to just point this out because really what we do with this new path recording oracle is we develop a unitary analog of this compressed oracle technique. So this compressed oracle is a way that you simulate queries to a classical random function. And the path recording oracle is going to be how you simulate queries to a Haar random unitary. All right, so now let me just jump into defining the path-according oracle. So the path-according oracle is going to be an isometry, and it's going to act on two registers. So one register, this cat_x register, is going to be an n-qubit register. So this is the standard register corresponding to the adversary's queries for the unitary. And it's going to have this additional register in red. That's the purifying register. It's going to be hidden from the adversary. And the purifying register is going to contain these set states, these ket_r states. So R is going to be a set of ordered pairs x1, y1 up to xt, yt for net. And these x's and y's are going to be n-bit strings. Okay? And so when I write a set inside of a ket, all I mean is that's just me labeling these vectors by sets. So two vectors are orthogonal if and only if the sets are different. Again, so because this is an isometry, it suffices to, if I wanted to find PRO, I just need to tell you what it's going to do on a set of orthogonal basis states. So on every state x tensor R, the way that this oracle acts is it's going to output a superposition over all y, well, almost all y. It's going to exclude the y's that have already appeared in the set so far. So y1 through yt are excluded. But other than that, it's going to sum over all y. And so it has a sum over all y and tensor product with R union of the singleton set xy. Okay? So again, it's taking xr. It's going to replace that x with a superposition over all y except for a few. And at the same time, it's going to insert xy into this set. And you should think of this as kind of analogous to how, when you sample a random y in the classical lazy sampling, you have to store the ordered pair xy for later. So I said this is an isometry, and to be a little more precise, there should be a normalizing term in front. This is actually a unit vector on the right-hand side. I'm not going to prove that it's an isometry, but just to get some intuition, why is this plausible? Just notice that this term on the right-hand side, this y tensor R union xy, uniquely determines xr. And this is because y is promised to be distinct from all the other y terms in the set R. Right? So when you have that y, you can look up the ordered pair xy and determine the original x. So at least this should convince you that this map is reversible. And if you're if you sit down with it, I promise you can convince yourself this is really an isometry. It's like a physical operation. And if you work a little harder, you can show that there is indeed an efficient implementation of this map. Okay. Great. So this is the only technical thing you need to understand before I can make my before I can state the main claim about efficient simulation, which is the following. So let's say you want to understand this picture on the left. So you have an arbitrary oracle algorithm A. That makes repeated queries to a Haar random unitary U. Okay? And so you have at the end the state ket AU, A superscript U. And this is the state of the algorithm after it's made some number of queries to a particular unitary U. And let's say that you want to understand what is this mixed state when you average over a Haar random U. The claim is that there is an equivalent way, or an almost equivalent way to think about this state by simply replacing every application of the Haar random unitary with a call to this path-according oracle PRO. Okay, so the main claim, and this is by no means obvious, is that the mixed state on the left, this expectation over U sampled from the Haar measure of ket bra AU, is close in trace distance, inverse exponentially close in trace distance, to the mixed state on the right that you get from replacing all of these calls to the Haar random unitary with applications of this path-according oracle isometry. Okay? So again, this state on the left is a mixed state because you're averaging over a Haar random unitary. And the state on the right is a mixed state because, well, you have a global pure state, and then you're tracing out this ancilla register. Right. So I'm going to sketch the proof of this claim in just a moment. But before I do that, I first want to just work through two really quick examples to give you some intuition for how this can possibly be true. So first example, maybe the simplest thing you could possibly do, is just query the unitary once on the all zero state. Okay? So if you do this, well, the mixed state that you expect to see is the maximally mixed state, right? U applied to 0 when you average over the Haar measure is the maximally mixed state. And so I'd like to show that I get the same thing when I query this path-according oracle. So when I query the path-according oracle, by the way, I always instantiate the set register to be the empty set, so this phi. what I'm going to get after one query is, according to the definition of the path according oracle, this uniform superposition over all strings y, like nothing is excluded yet because the set was empty. So this uniform superposition over all strings y of ket y in tensor product with a singleton set that stores the ordered pair 0y. And really, you can just ignore all this like set and like ordered pair notation at the moment. This purifying register is just recording y, right? So this is the maximally entangled state. And then when you trace out the red part, you're going to get the maximally mixed state. Okay, so in this case, they're actually exactly the same. Okay, slightly less trivial example. Imagine that you do 2 parallel queries on the all 0 state. So your final state is going to be u0, tensor u0. And then you average this over a Hall-random unitary. Well, it turns out this is the maximally mixed state over the symmetric subspace, which is just the linear subspace of all states that pass the swap test, so the states that are invariant under swapping the two systems. Okay. So restricted to this subspace, this is the maximally mixed state. And now you want to show that you get essentially the same thing when you replace those 2 calls to the Hall-random unitary with 2 calls to the path according oracle. And I claim that if you just follow the definition of the path according oracle, the state that you're going to get at the end, the global state, is going to be the superposition over all strings, all n-bit strings y1 and y2 that are distinct, of ket y1, y2 in tensor product with a set that records the ordered pairs 0, y1 and 0, y2. Again, you can ignore the 0 part. This is just a set that records y1 and y2. Right? And so if you trace out or measure this purifying part, well, you're going to get a randomly distributed set, like a random set y1, y2 of like distinct elements. And of course, like once you get y1 and y2 as a set, the remaining system is going to collapse to the superposition of things that are consistent with this, which is going to be a random state of the form y1, y2 plus y2, y1. Right? Those would be the 2 things left in the superposition. Okay? So this state is swap invariant, so it's in that swap invariant subspace. And it turns out that these states are nearly an entire set of basis vectors for the symmetric subspace. Like the only ones that I'm missing are the vectors, the states of the form y tensor y, where like y is equal to y. Right? But those turn out to just be an inverse exponential fraction of the total basis vectors. So this is actually very, very close to the maximally mixed state over the symmetric subspace. So I could keep doing examples all day, but the theorem is true, so they will always be really close. So at this point, I'm just going to sketch the proof of why exactly the path according oracle gives a valid simulation of Hall-random unitaries. And so this is going to be a proof by a hybrid argument, where I'm going to take any arbitrary T-query oracle algorithm and go from, at the very beginning, queries to a Hall-random unitary, and by the end, I'll have replaced this with queries to the path according oracle. All right, now you may be wondering, like where are PRUs going to come in? It's going to turn out by magic that the same proof will also show the existence of PRUs. So we're going to do both things at once. OK, so hybrid 0, we're going to start with the algorithm. So I'm just going to zoom in on the thing that it's querying. The algorithm is making queries to a Hall-random unitary. So that's the starting hybrid. OK, the next hybrid is I'm going to make queries to not a Hall-random unitary, but p times f times a Hall-random unitary, where p is a random permutation applied in place. So it looks like this, a random permutation matrix. And f is a random diagonal matrix. So here, capital N is like 2 to the little n. So these are exponential size matrices. Okay? And the point is that because the Haar measure is unitarily invariant, then u and pfu are going to be identically distributed. As long as you compose u with like any random unitary that's sampled from any independent distribution, it's still going to be Haar random. Okay? So u and pfu, exactly the same distribution. Okay? It just turns out that it's going to be convenient to exploit this unitary invariance to pull out this random pf and kind of use this for the next part of the argument. Okay, so hopefully this hybrid is easy. Okay, the next hybrid is we're going to now replace the classical randomness with a purification. So instead of sampling a random permutation p and a random function f, I'm going to introduce an ancilla register, an exponential size ancilla register that's going to contain the entire description of a whole permutation p and the entire description of a whole function f. So this purifying register is going to be initialized to the uniform superposition over all p and all f. Remember, these are exponentially long. And I'm going to replace this application of random pf with an application of controlled PF. So it's an operation that's going to read this register in the standard basis. It'll read the particular P and F, and then apply that operation to the main register. So again, this is like a set of perfectly identical hybrids. Like from the adversary's point of view, if you don't see that purifying register, if it's measured, then you're just going to see like a random application of PF. All right, so those are the easy hybrids. The next one is going to be quite a bit trickier. But I claim that actually you can replace this controlled PF with queries to this path-according oracle object. So I'm not going to be able to like fully explain this step, but here's like the rough intuition for what's happening. It turns out that for any set R, any set of ordered pairs R, so ordered pairs x1, y1 up to xt, yt, there is a way to define a particular state, phi sub r, and where phi sub r is a state on this PF register. It's basically like a different set of basis vectors for this PF register. Like instead of the standard basis of states indexed by PF, I'm going to look at it in this basis indexed by these phi sub r vectors. So just you'll have to believe me, there is a way to pick these phi sub r vectors such that the action of controlled PF, like the effect of controlled PF, can be understood to be the following: that on these phi sub r vectors, if you apply controlled PF to x tensor phi sub r, the output state is going to be of the form superposition over all y that have not appeared in R so far of y tensor phi sub r union xy. So I claim there is a way to define these vectors, and kind of if you write out this full purification, it sort of falls out naturally. And so what this is saying is, like, if you look at this expression, it looks like controlled PF is behaving exactly like the path-according oracle up to relabeling these phi sub r vectors as ket r vectors. Right? If I replace these phi sub r with ket r, this would be exactly the definition of the path-according oracle. Okay? The only thing is, I lied a little bit. These phi sub r vectors aren't fully orthogonal, so you can't exactly just like relabel them. But it turns out that like a large subset of them is orthogonal, will be orthogonal to each other. And it turns out that composing this operation with any unitary U sampled from a 2 design makes it hard to find these non-orthogonal ones, these non-orthogonal R's. Okay? So in particular, you can show that you can only put at most negligible weight on these problematic R's. And so for most of the R's that you're putting your weight on, they actually are orthogonal, and you can do this relabeling. So the point here is that if you look at the purifying register in a different basis, there is kind of a compressed representation, right? This R is a much smaller state. It's just like it scales with the number of queries t rather than being exponentially long. And there is a compressed representation that makes it easier to understand like what exactly a controlled PF operation is doing. And it turns out to be this path-according oracle object. Okay? So this is like one of the main proof steps. The last thing you want to do is you actually want to get rid of this unitary U. And it turns out that this definition of the path-according oracle, once you expand it out, you can show that it has the following like magical property, that if you make t queries to the path-according oracle composed with any fixed unitary U, this is actually completely identical to making t queries to the path-according oracle without the U, followed by applying U to the tensor t to the purifying register like afterwards. And this is kind of related to this like EPR ricochet property, where like applying one operation on one side of an EPR state is equal to applying like the transpose on the other side. It's kind of the same idea that goes into this. It actually might be transpose or bar or something. But the point is that this extra operation on the purifying register is completely invisible to the adversary, and you can delete it. OK, so this is how you argue that queries to a Hall random unitary are indistinguishable to queries to the path-according oracle. And now here's how you get PRUs. Notice that hybrid 2 to hybrid 4 works for any unitary sampled from any 2 design. And there's actually 2 natural choices of a 2 design here. One is you can plug in a random Clifford, and the other is you can plug in a Hall random unitary. And by a triangle inequality, you go from hybrid 2 to hybrid 4 back to like hybrid 2 prime. You can show that queries to PF times a Clifford are indistinguishable from queries to PF times a Hall random unitary. And the distribution on the right, like PF times a Hall random unitary, is just another Hall random unitary. And finally, if you replace P and F with pseudo-random objects, pseudo-random permutations and pseudo-random functions, you get the desired claim that you have an efficient distribution indistinguishable from Hall random. OK, almost out of time, but let me just say this one thing really quickly. This path recording oracle gives a new way to really analyze Haar random unitaries, especially in the setting of quantum algorithms. So there's this new meta approach here that just says, anytime you want to prove a statement about quantum algorithms that use a Haar random unitary, you can just prove that same statement but plugging in the path recording oracle instead, as long as you can tolerate an inverse exponential error. And this can be significantly easier than bounding, just explicitly bounding higher moments of a Haar random unitary using things like the Weingarten calculus. And already there's several applications. In our appendix, we showed this gives an elementary proof of the Schuster-Haferkamp and Huang gluing lemma, which is used to compress the depth of, generically compress the depth of random unitaries. And recent work of Anant et al. Shows a number of applications of this technique. One of their applications is to show that you can generically compress the key length of a PRU. So I think there's lots of exciting future directions. I'm basically out of time, so let me just put them up on the slide and say thanks.
Time for one quick question.
Thank you very much for the nice talk. Basically, what you showed about the analysis seemed to indicate that the error comes from the missing of basically the diagonal terms, the tensor products of, if you think about parallel queries, the tensor products of y, tensor y, etc., which corresponds to the requirement of recording only, sequences of paths, only paths that don't contain twice the same y.
Yes, yes.
Can you say something about how this helps you? Because this apparently introduces the error.
Yes, that's a good question. Yeah, so the question is kind of what exactly is going on with this error? How does it, why is it advantageous to have an error? Yeah, indeed, we have representation theory that exactly describes what happens when you query a Haar random unitary. And if you want to work really hard, I believe it's possible. I think there is a work that gives a space-efficient purification of a random unitary that uses representation theory. I think what the point is that sort of throwing away these colliding paths makes it a lot simpler. That this particularly simple representation of the path recording oracle is only true for this these non-colliding paths. And I think that if you wanted to get the exact one, you would have to have a lot more branches to the path recording oracle. And I think it would be less useful as a proof technique, maybe. Yeah, I think that's all I can say about it, though.
Let's thank Fermi again. And if you have other questions, you can catch him later.